So let me maybe pass the microphone to the first speaker, who is Vadim Kantorov. Vadim is originally from Yekaterinburg, from Urfu, Rural State University, math department, and after that he has moved first to France, first to NS Kashan, and then to INRIA and École Normale Supérieure, where he's now doing a PhD in Ivan Laptev's group, and he will talk about very recent work on video and
supervised localization.
Supervised localization.
Actually, do we need a mic? Or?
Yeah, it's better if all the speakers use the mic because of actual recording and the sound from the mic is also recorded.
Okay, cool. Hi everyone. So also don't hesitate to let me know if something about the sound quality. Okay. And also if you keep this informal, just bump up if you have questions. But I try to go slowly, given it's the first talk in the morning. So nothing extremely difficult. So this is our ECCV paper this year, and it's about weakly supervised localization using deep learning. And this is a joint work with my colleagues. And as you can see, Maxime prefers not to put any pictures of his online, so it's just a GitHub profile. Yeah. And so let's jump in. So to give a quick recap, the task of weakly supervised localization and detection, it means that we aim to localize objects, that is to find bounding boxes. And in train time, we have only labels for the whole image. So for this simple example, it means we know in train time that in an image there's somewhere a horse, somewhere a person, and we know that there are objects of other classes that are absent. And in test time, we want to produce the bounding boxes for every class. And concerning terminology, I say localization where for every class we just want to find the most confident object, and detection if you want to produce more of them. So now let's see why the task is hard and what kind of examples we can get with the existing methods. So here in the here I show some detections of existing works, and the left is the state of the art before our work at the time of submission. And I don't know, like, can you see the objects and the bounding boxes? Maybe not so well. So these are the cases where everything works fine. So like expectly with easy backgrounds like airplane right on the sky, it's very easy to detect the object, and the same sometimes like the car on the road, and so you can expect that things like that would work. So now some cases why we are interested in this task, and you can see some failing regimes. So one failing regime is so take this the top left image. It's a cat, and the ground truth is depicted using the yellow box. So, but the algorithm would produce a box which focuses on the face, and the same for the horse. So this like shrinking going on to the most discriminative parts of an object. So that's one failure mode, and the other is in the cases where context is very helpful for finding an object in the image, like yeah, we would have expansion, right? So the boat we leak onto the background, and so here, yeah, sometimes some scenes like the living room, or like when we want to find a table or a sofa, it would like to include the chairs around, or sometimes the people around. So like this is what we want to advance in solving these cases. Yep. So how can we hope to solve those? So an old idea, which was applied for like since long ago, is to reason about an object using context more explicitly, using its surrounding, and that's what we will try to do for this task. So this has the idea of processing and like what we think is an object and its surrounding separately has also been helpful for unsupervised object discovery work, which is yeah, the paper of Minsu. And that's what we'll try to apply this idea for weakly supervised localization. Sorry. Yeah. So what we want to assert is that like this would be our hypothesis. We would like to try, whether it helps or not for this task, is we would say that an object proposal is a tight bounding box when the contrast of class activation, say, we would have some function that gives us a confidence score on an object proposal, and if we can evaluate this function, the class activation score on the surrounding of an object proposal. So if we can have such a function, then we can measure the contrast between these activations, and we want to say that there's a higher chance that there's this object proposal is tight if this contrast is maximized. So it means that, so say I'm just standing here and you have an object proposal, like if you're lucky, right? So you have an object proposal just around my body, and then a function, ideally, it would give a high score when it's evaluated on the inside of such a proposal, and we would like that it gives, you know, some zero score or negative score when evaluated around, because there's no person pixels. And also, before I go into details, I'd like to add a bit more about motivation. Is that in weakly supervised regime, all that an algorithm knows is that it has a collection of images, and all of them have the same object, right? They share this object of the same class, but the algorithm doesn't know what we are interested to find. So say we have a few hundred of images with the person, and then we give it to such a weakly supervised system to find some object, right? And the algorithm a priori doesn't know if we're looking for a person, if we're looking for a face, if you're looking for nose or eyes, and for some types of objects, it may be like this contrast criterion makes sense, such as like maybe rigid object classes. And to help algorithm, we want to add this contrast constraint to guide it towards what we want it to find. Before I explain our contribution. I'm going to review this previous work on which we base our modification. So this would be a deep learning model. So the base architecture is fast RCLN. That means we have some external source of object proposal, say selective search windows, around 1,000 of them, and then first we are putting our image through a stack of convolutional layers, which will produce us a feature map. Here, right? So that would produce us a feature map of like 256 feature maps of a certain size, and then using these proposals, we are going to pull the feature values, and then we will put them through fully connected layers. So this is standard fast RCNN architecture. And then, so Bilen and Vidali, what they do is that they split into two branches. One branch, the classification branch. So it would take every an object proposal and its corresponding FC7 features, right? Then it would learn an adaptation layer, which would say give the confidence score for every class. And then they have the localization branch, which will learn to do selection among all those proposals. So why I say it will learn to do selection is that so they would have this fully connected layer that also produces for every class some score, but then they do softmax across all the proposals. So that would make a score from 0 to 1. So in the ideal case, this would make the object proposals compete against each other, and like the good ones should have the score closer to 1. And then what they do is that they mix classification score with these localization scores by doing element-wise multiplication, and then they sum across object proposals. So basically all it does is that it takes a weighted average of classification scores with the weights being the localization scores. So here is no contrast. So we are going to modify the localization branch to evaluate our contrast criterion. So here, as I said, the classification branch goes untouched, and we are going to modify this localization branch. In order to evaluate contrast of class activation of pixels inside the proposal and outside, so we are going to need to modify the pooling layer, right? So still we have the selective search windows, and then we are going to pool the features inside the proposal and then outside, and then pull through the fully connected layers that are coming from the base architecture. In our case, it's like VGGF. And then we are going to learn separate adaptation layers for features within the proposal and in its context. And then the rest is the same. We're going to do element-wise multiplication, and we do the softmax here across the proposals. So it's very similar across this, except this localization branch modification. And this is just to visually give a hint, right? So the here, like if you have a proposal, this means like inside pixels, this means context, and like the third, I'm gonna talk about this in a minute. So we evaluated 3 different models, like 3 different modifications, and one is we are gonna learn a separate adaptation layer for the pixels, so for the pulled features within the proposal and in its context, and then we're gonna add the 2. And then, so this is not contrast, right? But like one could hope that this would be equivalent to explicitly enforcing the function to evaluate the contrast. And here we actually do the contrast. So in the A model, we are gonna share the weight of this adaptation. So it's just one layer. And then we are explicitly going to do subtraction. So this would compute the contrast between class activation scores within an object proposal and in its context. And then one could notice that since the weights here are shared, and one may as well give as input to this layer features that have same distribution. So in this case, it means that we are gonna just instead of putting the ROI transformation, we're gonna put a small hole inside here, such that this layer, like during contrast computation, both its inputs would have similar properties, like they all have like a small number of zeros in the center. And so coming to the numbers, it's helping, right? It's helping. So here are like the previous works. So this WSDDM SSW is the work of Hakan Bilen, which was state of the art at the moment of submission. And what we're going to look here is the row F, which is our reimplementation of Hakan Bilen's work. So we had to reimplement because back in the day the code was not available, but it reaches the same accuracy levels as their paper. And we could see that by doing this contrastive S, we are gaining 5% of core log and 6% of mean average precision. So actually, I must say what are those metrics, right? And what's the data set? So here are the results on the dataset VOC7, which has 20 classes, and it has like 5,000 images for training subset and also 5,000 for testing. And mean average precision is the standard object detection performance metric, accuracy metric, and we evaluate it on the test set. So like those images are never seen in training. And one can also evaluate core log, which is standard for weakly supervised localization literature, and it is we are going to take for every class we are going to take positive images for that class, so they contain an object of this class, and then we are going to take the most confident detection of our method, and then we are going to test if our produced detection sufficiently intersects with the ground truth. So this is core log, and core log we evaluated it on the train val subset of the dataset, but still, since like in training time we don't get to see the bounding boxes, one can do that. And here, so like yeah, the improvement is quite big. And the fully supervised method for this task would achieve. I think Vittorio Ferrari said that like if you do the same VGF based model, you're going to get around. He said 65 or 70 MAP. So we're climbing up to half of what one gets with the fully supervised method. So there's still a long way to go, and there's still lots of failure cases. And here are some detections, and of course there's some cherry picking, and as you could see there's still lots of failure cases, like from the accuracy numbers, and we fixed the cat, we fixed the boat, we fixed the horse. So that's something to be proud of. And also we evaluated our method on a larger data set, VOC12, which is twice larger, and we still get the same. We still enjoy the same improvements. And here the test set is not. The bounding boxes are not publicly available, so one has to submit to the server, and we've done that to get the MAP numbers. So just to give you a gist of the how long it takes to train this model. So for the contrastive S, it takes just around 1 day of training on a single GPU, and so the rest is pretty standard. So the implementation was done in Torch, and so like for the more precise values of parameters, it's better to just jump in the code, because like different frameworks have different update equations and update rules, and like the exact numbers for the learning rates and such can be deceitful. We do also some basic data augmentation, just like in train and in test we randomly flip the images horizontally. So we can talk. What about the time? It's okay. Okay, cool. Because I have some reflections on what still can be done, and there's still, you can see, there's still a huge gap between like strongly supervised methods and weakly supervised, so often one can get some intuition from fresh fully supervised like segmentation methods and fully supervised detection pipelines, and sometimes like you can borrow the advances and apply them, but sometimes it just fails terribly for a weakly supervised regime. For instance, I wanted to try to use the RFCN work, which was like second or first for instance level segmentation on Coco this year, Coco challenge. And what they do is that they move the pooling after the fully connected layers. In their cases, they use a different base architecture, but still they put the pooling at the very end, and they're still able to not lose accuracy. And like if you just try to do this for this weakly supervised regime, it just fails completely. And so like you do some hacks, and still you still see like a dramatic decrease, like 15% down. So this is like this first point, right? So waiting for 1 day is fine if you just do this, but if you want to reuse these detections in some other pipeline, you may want to be able to iterate faster. And if you want to use a more powerful architectures like ResNet, then it all becomes slower, and also memory-wise, very hungry. so it would be cool to put the pooling at the very end, but so that doesn't work so easy. So that's one thing that I'm looking into. And another is here we use the selective search windows as our proposal source, and like you know, in the modern detection pipelines, like people would generate the proposals on the fly within the architecture, right? And so one can ask if we can do the same here, and also if one can try to do SSD style pipeline where one predicts a bounding box for every location. So this I'm interested in to try, and have, like if you are interested into Big Soup, and so come talk to me. And yep, so this is all, and code is online, and like just one thing, contrast can be useful, and that's all. Thanks.
Good questions?
What's the average speed of recognized layers in your algorithms?
So the question about the performance.
What's the average speed for learning to recognize some different layers?
So actually, we fine-tune the whole thing. So and we use VGGF network, which is similar to AlexNet. So we get around during learning, it's 4 frames per second, 4 images per second. And so the main factors here are how many proposals you are using, because like the fully connected layers take maybe half of the computation time. So that's why I'm interested in this speeding up. Because if you put pooling to the very end, you can use as many as you want without, linear dependency on the computational cost.
Okay, I have some peaks with 3 or maybe 4 layers with different points to recognize on my face. Yeah. Yep. How much time to learning to recognize about 2,000 points on my face in your algorithm? No, maybe average speed. Yeah.
So, about the task you described. So,
I want to recognize 3,000 or 4,000 points on my face.
Yeah, but like in weekly supervised regime. So. So here, like still like if you are using a lot of proposals, right, a few thousand, so this would be the same speed, like a few frames per second within this pipeline. So and we can talk offline.
Okay. Any other quick question?
I mentioned that you assume that any trained image contains only one object of the same class.
Well, so like when you evaluate for MAP, it's like the standard detection evaluation metric, and we actually able to produce a lot of detections. And then you just need to sort them or like prune them. And so, yeah, so there's no limitation on the number of police detections.
When you are training your algorithm,
yeah.
you choose context and assume that there is only one object and other types are context.
So like the way softmax would work is that if there would be a few detections which have the similar score, right, it would split like it would assign them score 0.5 and 0.5, right, in the localization branch. So it can work, and but then the problem is if like, the objects are too close together, and then that's failure.
Okay, thank you.
And you can also talk about.
Okay, thanks a lot.